Hello everyone, my name is Farnaz Jadbali and I'm the Product Marketing Manager for MSC Nastran and Mark. Today we would like to talk about the new MSC Nastran release 2018.2. The webinar title is Accelerate Your Powertrain Simulations by up to 3 times with the new AVL Excite interface of MSC Nastran. With us we have Raj Dua, Product Manager for MSC Nastran. I would like to thank everyone for joining this webinar.
Hi, and good morning and good afternoon, everyone. My name is Raj Dua. I'm the Product Manager for MSC Nastran. Today I'm here to introduce you the 2018.2 version of MSC Nastran, which will be released in the next coming weeks. Okay, so the topics that we will discuss today are listed on this slide. I will introduce the new enhanced AVL Excite interface, and then I'm going to hand the presentation over to Farnaz to talk about the rest of the enhancements. Okay, so let's talk about the new MSC Nastran AVL Excite interface. AVL Excite is a multi-body dynamic simulation software which is generally used in the automotive industry for excitation, to study the excitations in the internal combustion engines. It's widely used for powertrain simulation. For a really long time, our customers were using DMAP alters to interface with AVL Excite. So in this release, we've added an automated interface to AVL Excite. I'll explain what that means in the next couple of slides. So as I mentioned earlier, today there's a lot of reliance on DMAP alters, and what that means is it results in multiple large intermediate files that require translation. Also, even with the DMAP alters, currently there's no way to support the interface in Solution 400. The large intermediate files that are created via DMAP alters can result in large disk usage, and those files are generally of really large size as well. So there was multiple pain points that we wanted to address for our powertrain simulation users. So what we did is in MSC Nastran 2018.2, we created an efficient and streamlined workflow to directly export the .exp file, which is an input file that AVL Excite program can read in. So there's no requirement of using DMAP alters anymore. MSC Nastran does this automatically. There's no need to create large number of intermediate files. I will show some benchmark data which will show how the files generated are really small in size now, and the whole workflow is much faster as well. We've also added the SMP scalability for mass invariant computation, and I'll show some benchmark results in that as well. Some of the supported workflows are sound radiation, so to understand what the engine sounds like. Also, if you wanted to do a durability analysis after receiving the excitations from the AVL Excite powertrain model, we can also do that in MSC Nastran. And finally, one of the most exciting enhancements is the Solution 400 workflow for nonlinear powertrain dynamics. This is a brand new workflow. This was something that you couldn't do that in MSC Nastran even with DMAP alters. So here's the typical workflow for studying the sound radiation in your powertrains. Generally, our customers start with a Nastran finite element model, and then you do a Solution 103 type analysis with ACMS to get your mode shapes. And then those mode shapes are going to be transferred at the intersection points in the AVL Excite program to get the time domain loads at the intersection points. And then from there, we go to step 2, what we call step 2, in which you come back to MSC Nastran to complete your Solution 111 or 112 type of workflow, and then you get surface velocities and other data recovery as needed to perform a sound radiation study. So the new interface after step 1, when you run a Solution 103 type analysis, it will generate the .exp file for you, which can be read in the AVL Excite program. And then the file generated by AVL Excite can be brought back into Nastran and quickly transformed from time domain to frequency domain if you're doing a Solution 111, or you can keep them in time domain for solution 112. The solution 112 workflow is shown on this slide. It's very similar to the one we just talked about. In this case, we can also go ahead and do a durability analysis. Durability of fatigue analysis can also be done inside MSC Nastran itself, since we have embedded fatigue modules. The new solution 400 workflow is very similar to the solution 111, 112 workflow. In this case, we'll do an allostatic workflow, an allostatic analysis first, and then a linear perturbation step, and then followed by data recovery. And we can do the solution 400 powertrain vibration. So here we're comparing the two workflows, the old DMAP alter-based workflow, which you may be used to, and the new workflow shown on the left-hand side. As you'll notice on the right-hand side, in the old workflow, there's a number of assigned statements because a large number of intermediate files are required. These files can generally be large in size and result in high disk usage. And then you also had to use a DMAP alter to generate the EXP file. However, you'll notice on the left-hand side in the new workflow, there's only one command now. We've added the AVL EXP entry, case control entry. And then you specify EXP body is yes. In this, it generates a .exp file automatically. There's no need to generate or handle a large number of intermediate output files. Also, one problem with DMAP alters was if every time the version was changed, it may have required to update the DMAP alter as well. However, in this case, that problem has been taken away. We also use external superelement generation, which results in low file sizes and quick performance. This is a step 2 workflow for data recovery. Again, as similar to the previous slide, we're showing the old DMAP alter-based workflow on the right-hand side. Again, you'll notice in step 2, one of the problems was you have to define a dummy excitation to properly do a frequency analysis. However, in the new workflow, there's no need to do that anymore. On this slide, we're showing a typical solution 103 step 1 input file for MSC Nastran. You'll notice the assigned file and assigned statement on top is where you assign your OP2 file. And in this OP2 file, you can add all the OTMs and whatever data is needed for the AVL Excite workflow. Anything in red is what is required to run step 1 here. On the right-hand side, you'll notice the ACMS solution right there with the ASET points defined. We're also using the external superelement format. So in this case, we recommend user to only request output for the sets of physical quantities that are of interest. So generally the displacement and velocities on surface nodes, and you can add those to your OP2 file. This is a typical step 2. In this case, you'll notice that we're reading back the OP2 file with the super element databases, and then also the AVL Excite output. Here you'll notice that you have to define the frequencies of the time steps that match the number of frequency steps in the AVL Excite file. Just want to make sure that I point out that this is very similar to any external superelement workflow that's typical in MSC Nastran. So we've leveraged the existing kind of workflow for this analysis as well. In the standard TPL directory, you will find some of the example files that we have added for step 1 and step 2. For step 1, it will be named something like crank 103, and then for step 2, it will be named 111 or 112, depending on what solution you're looking for. For a typical 400, solution 400 input file is very similar to the 111, 112. In this case, first you have to do an NL statics and then a linear perturbation step. which is shown on the right-hand side. Otherwise, the workflow is very similar. And as you'll notice for step 2 as well, it's identical to a 111 and 112 workflow, so very easy to use. Again, some of the example files that you can find in the TPL directory are noted in this slide. So just some of the benchmarks. We couldn't show the model. These are customer models, which we were allowed to show. However, the model characteristics for this one, 10.7 million degrees of freedom. We used a buffer pool of 120 megabytes for this analysis and an SMP of 20. And as you'll notice, we ran it with the old DMAP alter workflow and the new interface workflow. And as you can notice from the plots shown on this slide, for the total time that it took, it was about 3 times as fast. And the total, the size of files that were generated were about 15 times lower. So a lot of intermediate files were removed. We've noted where the 15 gigs come from on the left-hand side in the old DMAP alter workflow. In the right-hand table, you'll notice that the reliance on those intermediate files have been removed, and the total time and the file sizes are just really small. Really efficient way to interface the AVL Excite. Here's another model that we were able to run. In this case, the total time savings were of much higher magnitude. Generally, we say the performance improvements that we've seen are about 3x on average. In some cases, it'll be really large, as shown in this slide, where it's almost 10 to 15 times. In some cases, it will be slightly lower than 3 times, but on average, you should see about 3x improvement. Also, if you're using higher order mass invariance, which typically takes a really long time to compute, in this case, you can use SMP of 20 all the way down to SMP of 20, and then we see over 6x improvement in scalability. So to summarize, we've created an easy and simplified user interface for our AVL Excite users. There's no more dependency on DMAP alters, and which improves the performance, reduces disk space, and also eliminates the need to update your DMAP alters to make them version dependent. In step one, we see the largest benefit for models requiring the higher order mass invariance. This is due to the SMP usage. We're also leveraging our external superelement format, which allows step 2 to be a true data recovery process, and is much faster to do. In step 2, we don't need to define demi excitations anymore, which also improves the performance. And finally, for virtual mass, we support both option 1 and option 2 in the new workflow. At this point, I'm going to hand the presentation to Farnas for the rest of the enhancements.
Thank you, Raj. So I'm going to be talking about the rest of the enhancements in Nastran 2018.2. We added some improvements to the frequency-dependent material properties that you saw in version 2018. Although these frequency-dependent material properties are very useful, the models have a tendency to get a little bit bigger. So in this case, using master frequencies would be a very beneficial option that we can see that it is possible to define master frequencies to compute the exact frequency-dependent stiffness matrix rather than at each individual frequency. This is to reduce the number of frequencies for generating matrices, especially for large NVH models. It's going to be very useful. So in 2018, master frequencies are defined automatically, so user does not have to do anything once the frequency-dependent materials are assigned. So all other intermediate frequencies, the stiffness matrix is obtained by a linear or logarithmic interpolation in the frequency domain. Only displacement, velocity, and acceleration results are available. And the master frequencies allow for a full solution for, as I said, displacement and acceleration results, and are chosen based on an M-freq tolerance, which is the default for that tolerance is about 0.1, and it goes across all the associated frequency-dependent materials. So you can see here that the user can decide to define their own master frequencies or use the automatic feature. So it's up to you. And this is available in both the direct and the modal frequency solutions. And here we can see in the graph that the solution with the M-freq equal auto, which defines it automatically, and the solution with M-freq equal to 1000, where the user defines, they both agree with the solutions that we got from the SOL 108 direct frequency response analysis. So the results are pretty good in comparison. Next, I will be talking about the dynamic analysis enhancements in Nastran 2018.2. So generally in Nastran, there are two types of damping that are available, two main types for linear elastic materials, the viscous and structural damping, and we all know about that. The viscous damping force is proportional to velocity, and the structural damping is proportional to displacement. Which type to use is dependent on the physics of the problem that you're solving and the chosen solution method. So when performing transient response analysis in MSC Nastran, specifically solution 112, because it's based on the real math, adding the complex matrix in the transient response solution with time domain is not allowed. So that means the user must come up with a way to convert their complex matrices into equivalent real matrices. In previous versions, the structural damping coefficient from W3 or W2 was required to do the conversion, and the conversion will happen only at one frequency, where these W3 and W4 are the only frequency that the viscous and structural damping were equivalent. Now in 2018.2, we have added a param W modal equal to ES, which will automatically produce the accurate conversion of damping at all frequencies. And this conversion is done using the modal frequencies based on the eigenvalues, as you can see below. This relieves the user from trying to determine the best value for param W3 and W4, and it's an efficient way to increase the accuracy for damping values. The next enhancement that I'll be talking about is the bar end loads and the panel shear flow. Calculation of internal loads data is very critical for design of airplanes and aerospace vehicles, and so it's especially for design of wing models, skin models, or frames. We see stiffeners are typically represented at this configuration. You can see it from the right-hand image. And the interaction between the stringers and the panels are reflected in the stringer loading and shear flow of the panel. So it's very important for people and beneficial to understand what happens at that area and understand the bar and loads. Lots of time engineers are interested to know these stresses and loads at the end of these elements. That's why we've added the bar and load capability. In addition, shear flow is also very important to know. So before, you had to extrapolate the results or use Patron to do such a thing, but now in Nastran, in MSC Nastran 2018.2, you can simply request for a case control entry BENDL, bent L, and that will provide you the results. So you have the option to print, where it will print the bar and loads and shear panel flows to DF06. You have the option to say no, you don't want to get those. And as a user, you have the option to assign a group of elements to obtain the results or you can just say you want to get the bar and loads for all the elements. Same thing applies to shear flow panel for the quad 4 elements. So here we can see a typical output. You see printed in the F06 file using the BNDL print option. And we can see the total end loads at N1 and N2 for the bar elements. And it's a very useful feature for, especially for aerospace. Next, I'll be talking about the rotor dynamic enhancements. In Nastran 2018.2, we have made enhancements to account for ground weight mass in rotor dynamic analysis. Weight mass is the scaling factor between mass and weight, and we're all familiar with that. This parameter was not reflected in rotor mass summaries in previous versions. In 2018.2, this limitation is removed, and now you can see the mass summary for 2D, 3D rotor that is calculated correctly and scaled by the weight mass parameter. And as you can see here in the slide, the results match the grid point weight generator output. So on the right-hand side, we see the grid point weight generator output. Similar capability has been added and corrected for unbalanced loads generated in frequency response analysis. And the unbalanced loads are now corrected and scaled properly. And you can see it is supported for both the fixed and rotating coordinate systems. Next, I will be talking about the contact model check. This is and some of the other enhancements that have been added to contact analysis for version 2018.2. The main one is the contact grid status check. This allows you to check the grid distance between contact pairs. I'll go in detail for all of them. Then we have added the functionality to display the geometry adjustments of initial stress-free contact. We also added the functionality to display the SD line output of contact surfaces when analytical contact is used, and a minor enhancement where the bias equal to 0 is now available and possible to enter. So let's talk about the contact grid status check, the con check. Contact analysis, we all know that is an important step in design of many auto and aero-related models and cannot be neglected. From the model assembly perspective, integrating various components is a challenging task and requires detailed analysis. So several scenarios involve internal geometry adjustments based on the initial configuration of the model. That can happen where you have initial gaps or overlaps, for example. We see that the initial stress-free can move the nodes to have a better configuration for contact. But in so many of these cases, the user needs to have a good understanding of what happened and how the solver changed it, and know the details of the contact models and be able to review these changes. So this makes it easier for you to make early design changes if possible. Now, with the contact model verification tool, you have the option to examine the contact conditions in early design stages and make changes if necessary. The new contact checks provide important information about the contact bodies and their initial status and the geometry in various output files. You can see here, for example, you can ask to provide the status of contact grid within a given tolerance. And we see here in the output that is sent to the FO6 file, this shows you the initial condition of the slave node. It shows you the contact surface. It shows you T1, T2, T3, which are the directions for the contact distance, the vectors. And also you can see the status, whether it's been penetration, there's a gap, or it's on surface. And you can lastly see the contact distance. And the negative distance means that penetrations have happened. So this is a very useful output that you can obtain, and one can also send these results to Patran or through the OP2 or the HDF5 for further post-processing. The second option that was added was the geometry adjustment to display the initial stress-free contact. There are so many cases where the models have initial gaps or penetrations at the contacting surface. In this case, the solver automatically, if you define initial stress-free, will provide special techniques to achieve this goal and move the nodes so there are no stresses at the very initial step. And this is important to note, and it's important to view this as a user so you can make sure that it is doing what you wanted it to do. Now, utilizing the 2018.2 version, you can now examine these geometry adjustments induced by the stress-free initial contact through HDF5 file. And you can ask it to be sent to the result files and then visualize it through Patran or other GUIs. Some examples that are available to view are the vector plots that show how much each node moved, or fringe plots that represent the geometry change distribution, as you can see. Now, for this release, this is only supported for node to segment contact, but in future releases, we have the option to add it for segment to segment as well. And this option is supported for all contact types and in all solutions, including permanent glue contact, general glue contact, touching, and all others. And it will definitely help you to check and make sure that the solver is doing what you really wanted it to do and the changes are reasonable. Similarly, we have added an option that allows you to visualize the output for the analytical SP-line smoothened surfaces. So when you have a curved geometry, MSC Nastran has an option to smoothen the contacting geometry for you for improved accuracy using analytical surfaces. This provides better continuity and eventually improved results. Now, the new contact model check allows you to view these plots, view these geometry adjustments in a plot and display them in Patran and verify and examine them and make sure it's doing what you really wanted it to do. It is again supported in all contact types for Solve 400, and in this release it's only supported for node to segment. In future releases it will be available for segment to segment. The smoothened surface can be output to HDF5 and OP2 files for further processing and through Patran or any other post-processor that you use. It is following the input format of BC nerves. If you want to look for more details, please visit the release guide. Lastly, we have added the option to quantify equal to 0 in Beacon, PRG, and BC table. Previously, if you wanted to define 0, Nastran was requiring you to enter a very small number, something 10 to negative 16. 0 was not working, and that would default the value for bias to the default value if you had entered 0. But in the new release, we have added the option to enter 0, which is very useful. Now, if you had old models that you had the 10 equal to negative 16, you might want to change it back to 0 so it's easier. Now I will be talking about the Solution 700 or explicit nonlinear solution enhancements. As you all know, in 2018, we had a major change in our Solve 700 solution. The LS-DYNA-based Lagrangian solver was replaced with the Dytrans Lagrangian solver, and the LS-DYNA is no longer available. This may have created some problems with material formats for some of you guys. The material formats that were based on LS-DYNA now need to be converted to MSC Nastran MathX material format. For user ease of use and for user benefit, we've added a translator that will allow you to get the old Dyna materials converted to equivalent MSC Nastran. The ones that are not supported, you will receive a warning message issued. As you can see here, for example, we have the Dyna-based anisotropic material for simulating sheet forming processes. This was not supported in the Deutran based, so that's why you see such warnings. Now, other than that, most of the ones that are supported, the translator will allow you to easily convert those. And we can also see that for user benefit, we've added a new DMAT D guide for you, available in MSC Nastran 2018.2, that is delivered with the documentation package. And this guides you through how to change these material properties, or you can see the materials that can and cannot be translated to the Nastran version. So here you can see some examples of the supported materials. The old Dyna rubber materials formats were MAT D027, and now you can see the equivalent Nastran format for rubber materials is MAT HD. If you have any questions, you can always review the release guide, or as I said, the DMAT D guide, or you can always call our technical support people, and they're very helpful to provide you more insight. Now we'll be talking about the HPC improvements in version 2018.2. First set of enhancements were for the Solve Auto feature. Previously, users had to spend some time and use trial and error method to figure out the best setting for running the job. With the 2018 version, which was last released, this changed. We defined a solve equal auto and a solve equal to terrain for you, which allows MSC Nastran to automatically select the best solver method and optimal configuration for the model. This is a very convenient way to run the job. You no longer have to decide and see what is the best memory or what is the best SMP or DMP option. Of course, you do have the option to do it yourself if you would like to, but the automatic way will save you a lot of time. The solver will examine your model based on the element type, solution size, and memory requirements, and select the most efficient option to run the analysis based on the solution and other options. The combined option solve equal auto selects the best basics model to solve for solver of your choice. Or for your 101 models, 103 models, 111, and other solutions. So in 2018.2, we have enhanced our learning capabilities to predict the required for the CASI solver as well. Previously, this was available for Paradiso, but now it's also added for CASI solver. CASI solver is a beneficial solver, iterative solver for solid dominated models. It's more efficient to use, and this is automatically selected. So the solver will notice that your model has a lot of solids and automatically select the CASI solver. And based on machine learning techniques, it will try to make predictions and get better and better after each run, as the solver learns from the previous runs and how much memory is required for your model to run. Now, if you feel like you don't want to use CASI because you don't like the iterative solver, you can disable this option by saying CASI equal no. Although this is available, it is not recommended because CASI is very useful for solid dominated models. If you decide to say CASI equal no, it will use the Paradiso or the MSC LVL solver for your solution. Additional enhancements to solve equal auto to improve performance of solution 108 models have been made. It will decide to choose the number of DMP cores based on the minimum between the number of CPU cores you have, the number of frequencies, and the ratio between the available memory to the estimated memory. Now, once this is decided by the solver, the remaining cores are assigned to SMP. This is very useful and improves the performance of small 108 models that have many frequencies. I'll show you some examples in next slide. The last option added for solve equal auto is that you can now define that in your individual RCF files This is very convenient as you don't have to define it each time for command line for a specific run. So once you define it in the RCF, it will allow the solver to use this option for all the models that you run with that version. Here you can see some examples for how solve equal auto improves performance of solution 108 models. Here we have a model with 500K nodes and 9 frequencies. So the model had 9 frequencies. It tries to pick the minimum between the number of frequencies and the number of cores of CPU you have and the memory ratio. So in this case, it used 9 DMPs for you. And you see how the new setting resulted in almost twice the speed in comparison to version 2018. So the 2018.2 ran in 54 seconds, whereas the 2018 ran in 99 seconds. You see how the system used 9 DMPs, and it had 20 cores, so each DMP processor allocated 2 cores for SMP as well. Another example that you can see here for solution 108 model with 3 frequencies. In 2018, solve equal auto did not use DMP because it did not have sufficient memory. In 2018.2, it did not use DMP as well. However, it gave the remaining cores to SMP. So again, it tried for DMP and then the remaining are to SMP, which will improve your analysis runtime. In this case, you see the new setting resulted in up to 4 times speed up for the analysis. The model runtime was reduced from 113 to 30 seconds. Another enhancement that has been added in version 2018.2 is related to the ACMS method. ACMS, or Automated Component Model Synthesis method, is an important capability in linear dynamic analysis for MSC Nastran. ACMS is the actual standard method of computing for a model subspace for the analysis, especially for the noise and vibration of large models. In 2018.2, we've improved the performance for ACMS to increase user productivity. As you can see here, a static scheduling method was used, which assigns the work to parallel threads that we have. Here you can see on the right-hand side, you can see this image. It shows you how the multi-threaded improvements in 2018.2 are working. This is done by default. The user does not have to do any changes. If you look, you can see that instead of looking at the top row sequentially and processing each of the dots in a serial manner, we now see that the new system, several SMP processes are used in this system. Each one computes a chunk of those dots. As you can see, the gray ones are computed, then the blue ones, and it goes further. This will improve the performance of the ACMS solver a lot, and it may require a little bit slightly higher memory, but it will provide a lot of improvement. Now you can see on the lower left side the comparison between, the lower right side. You can see the comparison between version 2018 and 2018.2. If you notice, the blue ones that represent 2018, at some point you did not gain any performance for using SMP, like SMP 4, 8, and 16. The blue shows the same height, whereas using the new 2018.2 with the improved ACMS performance, you see better performance as the SMP increases. So the best option is seen with the SMP 16 in this particular model, and which resulted to about 75% reduction in time. Last option that I'll be talking about is improved efficiency for solution 103 full data recovery models, where you see reduced I/O and disk space. We use, as we're showing you, is a test case model with 11.8 million degrees of freedom and 2,868 modes. As you can see, the I/O was reduced from around like 1,600 gigabytes to 443. This is a significant reduction. Here you can see some parts of the log file and the FL4 file shown to you, the comparison between version 2018.2 and version 2018. Similarly, the elapsed time for the same model was reduced from 48 minutes to 11.5 minutes. So this is added for user productivity to improve your efficiency for your Solution 103 model.